talk a little bit more about reflexes tonight, and then we're going to get into muscle. And muscle has multiple types. If you want to read ahead in the class, we're going to first get into skeletal muscle, and that's going to take a large chunk because we're going to look at a lot of regulation of skeletal muscle. And then we're going to look at smooth muscle and cardiac muscle so we can get into the heart. This is a roughly parallel lab. In lab, we're going to start measuring the heart next. But there's a lot of basics about muscle we need to cover first. So you guys tell me. Acetylcholine, made up of two little smaller molecules, an acetyl group and a what group? A choline group. And where do they get put together? Inside what part of the synapse? This is a mini test on synapses. In the presynaptic terminal. Janelle's got it. So we take acetyl coenzyme A and choline, we put them together in the presynaptic terminal, and we package them up in these little vesicles. That way we wait until the action potential comes. When the action potential comes down, it lets a little extracellular calcium into that presynaptic terminal, and that causes exocytosis, releasing that acetylcholine into the gap between two nerve cells. A skeletal muscle only works well when it's actually working in conjunction with the nervous system. And in fact, if the nervous system stops working, the muscles get no signals, the muscles just start to atrophy. So as we think about muscles, we're going to ask, how can this muscle actually pull on this leg to kick it forward? But then we're going to come back and we're going to talk about control of muscle, and it's all going to be about reflexes and actually looking back at what's going on in the central nervous system. Can you handle that? Because I don't want to lose you when we focus in on muscle. So we're going to zoom in on this tonight. Our lecture is muscle. That's what you told me you wanted to study. So we're going to zoom in on muscle here. We're going to look at different actions of how this muscle could actually do something like contract to kick this foot. The muscle gets its name because it's connected to the skeleton. Its job is when it shortens, it actually pulls on a skeleton or delivers force onto a bone. If I were to look at a muscle, and some of you guys have had anatomy. I didn't bring my demos today. Instead, you're going to have to squint your eyes and believe that I have a muscle here. So I have a muscle here, believe it or not. And that muscle's job is to have a whole bunch of fibers or a whole bunch of cells that are running in one direction here. When they actually get a signal, each one of those cells gets a little bit shorter. But the end of that muscle is connected up to my forearm and connected up here on my shoulder, so that when it actually contracts, it actually moves those two bones reference to each other. Now, I surveyed you at the beginning of the class, and about 60% of you said you had already had anatomy, right? Yeah? So, what's the name of this muscle here? It's the bicep. And the bicep's job is to pull this arm this way. The only thing a skeletal muscle can do is deliver force by shortening up. Skeletal muscles do not push. They only shrink or shorten to deliver force. So I have a series of skeletal muscles here, my biceps, that when they actually contract, will pull my arm towards me. Now if I want my arm to go away from me, what can I do? I can't push the bicep. The mechanism of contraction only gets shorter. But it just so happens that I have another muscle here that's on the back end of the arm. We call this a flexor, and this is an extensor, the tricep. When it gets the signal to contract, it pulls the arm in the other direction. So you guys have seen in both directions that muscles, if you've had anatomy, come in pairs, opposing pairs of flexors and extensors. Right? Good, I'm getting nods here. So the job of the skeletal muscle is to contract, and that's going to deliver some force onto the bone. Rather than you look at my muscle here, I want you to explore your own muscle. Find your bicep. Your bicep, not your neighbor's bicep. Find your bicep. Okay, you all got your bicep? Okay, now I want you to feel that muscle. How's it feel? Muscling? Feel pretty good? as you're feeling that muscle, is it tense?
No.
Is it totally flaccid? Notice it's somewhere in between. All right? Now, move your arm towards you, just feeling your bicep. Does the bicep feel like it has any more tension on it?
Yes.
Is it moving a little bit? I hope so, otherwise your arm isn't moving. It's shifting a little bit. All right, so do you feel your tricep? Is there a lot of tension happening on it? All right, we're going to try an exercise here that will be really useful when summer comes next year, because today is the first day of fall. I want you to all get used to, at the beach, telling someone where the bathroom is. So I want you to take your arm, I want you to point your finger up. I want you to point your finger away from you. And while feeling your arm, I want you to flex your bicep and your tricep at the same time. So if someone asks you, where's the bathroom at the beach, you say, it's over there. Do that. Contract both the bicep and the tricep at the same time. Over there. What do you feel? Contract? Let me set it over here. Is it softer or harder? Harder. Okay, we have universal acclamation. It's harder. If I contract the bicep and the tricep at the same time, both are pulling in opposite directions. And like a tug of war, you just build up tension. The job of each one of those skeletal muscle fibers is just to get shorter. But that doesn't mean their job is only to do motion or movement. A big job of skeletal muscle is just to give you tension where you need it. Right now, I am standing up here, opposing the force of gravity by about 6 foot 4 inches above the ground, because my spine has all sorts of tension on it that's just there holding my spine up. And that's because these muscles are contracting against fixed points. If I were to look at my bicep here, there's not a lot of tension in it as long as motion is happening, but if I were to fix the end of it and then contract, it starts to bulge up a little bit. Anytime something is fixed, the same contraction is pulling, but we're using that to do things like lift objects, oppose weights, push against the wall. All of those types of motions are employing our skeletal muscles, and the units of those skeletal muscles fixed to a bone to just either move something or develop the appropriate amount of tension to do something. And the unit at which that is done in a skeletal muscle fiber has one job, and that is, when told to, get shorter. Just looking at these things, they don't make any sense. So what I would like to do is I would like to talk about how contraction works, and then ask you guys to go read this with an idea of which one of these bands is going to change or move during contraction. Why do I need to know about these bands? Because I can't talk about what's happening unless I have a way to identify this part is moving here, this part is not moving. Does that make sense to you guys? So let's talk about how contraction works, but I want you to spend some time with your book being able to know what band is what, just so that I can ask you questions about it. So we can have an intelligent conversation about when this moves and what doesn't move. You actually can see the movement if you're looking at the banding pattern. So myosin acts kind of like someone in a tug of war. They stand on the ground, they're a big trunk, and they have hands. And those hands can grab a rope and can pull it. The rope is actin, hence we call it the thin filament, because it's much thinner with reference to how thick the myosin is. The myosin heads are going to grab the actin and actually pull it in a direction next to it, so that these two types of filaments are going to actually slide next to each other. Neither one of these proteins is going to contract. Instead, they're going to move next to each other by having myosin grab actin and pull it. You with me? Okay, now here I just got to get freaky on you here. Because the actual organization of a sarcomere, if you can imagine with me here, is like a tug of war that has been inverted. Imagine on this wall of the room, I had a rope sticking out here into the room. And I were to get 6 of the strongest students in the classroom to come up here and grab this rope, and when I said go, pull it in one direction, this direction, towards the center of the room. with me? Now imagine I had 6 more of the equally strong students. You've all been showing me your biceps. And a rope attached to this wall that sticks out into the center of the room. When I say go, these guys are going to pull in this direction. Like a tug of war with each other, but they're both pulling the ropes towards the center of the room. Now, if I were to set up such a situation and tell all of the students here, pull at the same time, what would happen?
They bump into each other.
The ropes would slide to the center of the room. The people would grab and pull, and hopefully the walls of the room would come towards the center, because they're that strong. Make sense? This is the job of the circuit